The Interested Reader podcast is about exploring the world beyond the textbook. We'll cover many lessons in math, physics, and astronomy, and then delve into the mysteries of the universe. Physics is fun, people just don't know it, and I want to change that. I want to spark your curiosity about the world around you and ignite your passion for exploring and questioning. I'm your host, Sarah Tyke. Come with me and let's take a random walk into the world reserved for the interested reader. Hi everyone, welcome to episode 5 of the Interested Reader podcast. Today our lesson is going to be a little bit about some notation that we'll see throughout the podcast and just kind of an introduction to vectors and scalars. And then the topic for today is going to branch off of that bit of a scalar lesson that we get, and we're going to start talking about scalar energy. Scalar fields, waves, energy. We'll probably do this in 2 parts. So today I'm going to give more of a background on what is scalar energy, what are scalar fields and waves, and then next time we'll go into a little bit more about the alternative medicine aspect of scalar energy. So let's go ahead and get started. So for notation, one of the things we're going to first encounter is a thing called delta, and that's going to be applying to derivatives. So delta is just our Greek symbol. Looks like a triangle. And that is going to be used to denote a change in something. So we're going to talk about a change in position, a change in velocity, and we're always going to symbolize it with this delta symbol. So for example, if you have an object moving from x1 to x2, we're going to say that its change in position is going to be delta x, so change in position, is equal to its final position, which would be x2, minus x1. So if you're on, just say your standard number line, from say 0 to 10, if your x1 is say position 2, and you move along to position x2, which is at say 8, whatever your units, 8 kilometers, 8 spaces, 8 blocks, whatever you want to call them, you would say here that your delta x, or your change in position, is 8 minus 2, or 6, whatever your units are, miles, blocks, squares, spaces. So this delta x quantity is what we're interested in. Most of the time that's how I'm going to say it. I'm not going to bother saying the change in x. I'm just going to say delta x, and that's what I mean. And this will also apply to things like velocity. I'll say delta v, and that is just going to be your final velocity minus your initial velocity. It's always going to mean a change in, and we're always going to do the final position or velocity minus the initial position or velocity. So to that end, we'll also talk about initial and final positions. So we do a lot of subscripts in math and physics. So initial position will always be denoted with a sub I. So we'll have x with subscript I. That will always be your initial quantity. And again, that can be velocity, v sub I, it could be acceleration, anything you want. The initial position will always have a subscript I. And then your final position will always have a subscript f. And that will always be your final position, final velocity, final acceleration. So then we're always going to have our change in quantity will always be final minus initial. All right. Sorry, I'm kind of distracted. My cat is up here getting into stuff, and I was hoping she would just leave, but I don't think she will. All right, so we have our change in quantity. That's our delta. So that is going to lead us into what is known as derivatives. So a derivative is a quantity that you obtain from some other quantity. You do a manipulation on it, say from position. You can get velocity from your position. You can derive velocity from your position. Same thing with acceleration. So what we're going to do, we're going to start with, we have our position x, and we're going to call, so you can see my cat tail up there. I'm real sorry, guys, but it's just easier to let her do her thing, I think. Velocity will be v, and time will be t. And these are kind of standard notations. X will almost always be a position. We'll use other variables for unknowns, such as a, b, c, but velocity will always be x. Velocity will always be v, position will always be x, time will always be t. So velocity is always going to be a change in position over a change in time. And we talked about this earlier when we talked about units. So we're always going to have a change in position, that's delta x, divided by a change in time, which is delta t. So again, our units say miles per hour. That would be miles divided by hour. You can have meters per second, kilometers per minute. You can do whatever you want. But it's always going to be some change in position over change in time. So we have delta x divided by delta t. And we know that delta x is x final minus x initial. And same thing with delta time, will be t final minus t initial. T initial is almost always going to be 0 because you're always going to be starting your clock at time 0, but it could be anything. So this is the breakdown for velocity. Now what we're normally going to do, instead of using deltas and instead of using final minus initial, we're going to use what's called a derivative, and that is going to be denoted by a d over dx. D over dt. So what this means is that we're going to be taking a derivative with respect to time. So in the denominator we have dt. That t is the variable that we are going to be taking our derivative with respect to. So velocity can be written as a derivative of x divided by a derivative of t. And how we say that is a derivative of x with respect to t. So in our case of velocity, we say that x is a function of t. So what that looks like is x parentheses t. And what that means is that our function of position is going to depend on time. So as time goes forward, your position changes. Your position is dependent on time. So x is a function of t. So velocity, as we take our change in position, we are taking a derivative of x with respect to t. So we've got our velocity is equal to dx dt is how I'm going to say that. So what that is it looks like a fraction, dx divided by dt. I'm going to say it as just dx dt. And probably the more correct way to write this is to put our d over dt out front and then put x of t. That's our function. So this lets us know for sure that x is a function of t and we're taking a derivative with respect to t, our independent variable. Okay. So that's going to be our first equation that we want to keep in mind, is that velocity is a derivative of x with respect to t. The next we're going to look at is acceleration. And acceleration is a change in velocity, so delta v, divided by a change in time, which is delta t. So our units here are going to be a length per unit of time squared. So it would be, standard is meters per second squared. And really what that breaks down into is meters per second, your velocity, divided by second, your time. And all that acceleration is conceptually is it's a change in your speed. And so we all know is when you accelerate in your vehicle, how fast are you changing your speed? How fast are you going from 0 miles per hour to 60 miles per hour. That's an acceleration. An acceleration, since we have a change in velocity with respect to time, is, we say that it's a derivative of velocity. So acceleration we can write as dv over dt. And again, just like with position, our velocity is a function of time. Because once again, time is kind of our constant. It just goes forward, and velocity changes depending on time. So this is our second equation that we want to keep in mind, is acceleration is a derivative of velocity, or A equals dv dt. Okay, so that's the basics for the notation that I want to cover right now. These are just the things you're going to see. It will be the deltas, the derivatives. You'll hear me say things like dv dt, dx dt. What that's really saying is a derivative of x with respect to t, or a derivative of velocity with respect to t. And if we really just, you don't really need to know this right at this second, but we can also say that acceleration, if you want to take your equation for v and substitute it into our derivative of v here in our equation for a, we can do that. So we'd have a equals, here's this d by dt, I'm going to put that out front, of our function velocity. And then I'm going to take and replace this v with our equation for velocity, which is dx over dt. So now what I have is a is equal to d by dt of dx by dt. And this is just written as d squared x over dt squared. And this you won't need to know this right this second, but what this is called is a second derivative. So you would say that acceleration is a second derivative of x. All right, so that is our basic introduction here to some notation that we'll be using. We'll just kind of add more as we go. It's kind of like adding vocabulary when you're learning a new language. So next we're going to talk about vectors. And one of my favorite applications of a vector, if you've seen the movie Despicable Me, the supervillain was named Vector because he is committing crime with both magnitude and direction. So that is our key definition here of a vector. It has magnitude, which is the size of the quantity, and direction. Okay, so we had a little bit of technical difficulty there. I'm not sure I'll be able to record an episode without some sort of technical difficulty, but maybe sometime in the future. All right, so here we are talking about vectors. So they have both magnitude and direction, as we said from our favorite supervillain Vector from Despicable Me. So our quantities that are vectors, and we were just talking about these in notation, I was a little bit incorrect, a little bit casual with my definition. Position is actually a vector. So position is represented by x. And you'll always, in text, you'll see vectors will be bolded, or they'll have an arrow over the top. So position's a vector, velocity is a vector, and acceleration is a vector. So all of these quantities have a magnitude. So your position might be, say, 5 miles, but you also need to say essentially from where. I'm 5 miles north of the bridge. I'm 2 kilometers east of the river. So you have to have a magnitude and a direction for position. Same thing with velocity. You might say that you're going 60 miles an hour. That's actually just your speed. Your velocity would be 60 miles per hour westbound, if you're going to have a true velocity, which is a vector. And same thing with acceleration. So this brings up the point that when we're talking about something like 60 miles per hour, it's really just a speed. And so speed is actually the magnitude of velocity. And then for position, its magnitude would be what we call distance. So just saying that you're 5 miles away would be giving a distance, not a position. If you said you're 5 miles north, then you have given a position because you've given a magnitude and a direction. So a lot of the times we're going to probably be talking about speed and velocity. They'll probably be used interchangeably. I'm sure at some point, you're going to hear me say that the velocity is 10 kilometers per hour. Very technically speaking, that is the speed is 10 kilometers per hour if I haven't given a direction. So that's the important thing about vectors, is that they need a magnitude and a direction, and that you'll see them denoted with an arrow over it. Or if you're reading a textbook, it'll be in bold print. Since I can't bold while I'm writing, I'll do the arrows. And essentially what we're going to be doing is we'll come into more of this next time with our other lesson. We'll start getting to the components of vectors. But I think for now, that's probably all we'll do for vectors. That's the main thing that we want to get introduced with. And then, like I said, next time we'll start talking about the components of vectors and how you can add them and subtract them and graph them out. Okay, so the other half of vectors is scalars. And we kind of talked about that just now with our distance and speed. So when we talk about the magnitude of a quantity, that is actually the scalar value. So that is magnitude only. So that would be what we call distance and speed. So whenever I say, or whenever you say something like you're 5 miles away, you've given a distance, a scalar quantity. There's no direction given. And same thing if you say that you're going 70 miles per hour, you've given a scalar quantity because you've only given a magnitude. You haven't given a direction. You've just said a speed. So that's just kind of a brief distinction between vector and scalar. And the scalar quantity is the magnitude portion of a vector. So those two are related. So that's all I want to say right now for our lesson. We'll talk again about vectors next time and do more actual manipulation with them. But for now, I just wanted to introduce you to them, the definition, the notation of them. And for the rest of the podcast here, we are going to start talking about scalar quantities called scalar field, scalar waves, and scalar energy. It's a pretty fascinating topic, and I am going to have to take a break here, and we will continue recording this a little bit later. All right, so today we're going to be talking about scalars in the context of scalar fields and scalar energy. So today we're going to do kind of a background of it, get some definitions, some vocabulary down, and then next time I'm going to talk about more about like scalar energy and the sort of alternative theories behind it, the alternative applications, and some experiments that you're not maybe traditional, but are, I think, really cool. So first of all, we need to talk about what is a scalar field. So this is a function that associates a single number to every point in space. So like when we're talking about vectors, we have a magnitude and a direction. Vectors have different components. Scalars do not. Scalars are just a single number. That's the magnitude part of your vector. So when you have a vector and you're talking about 60 miles per hour eastbound, the scalar portion of that is the 60 miles per hour. It's just a number. So when you have a scalar field, you have a region of space that has a single point, a single number assigned to every part of it. It could be just a purely mathematical, abstract, theoretical space, or you could have physical quantities like temperature or pressure. And this field must be independent of your frame of reference. So that would mean that two observers will agree on the value of the field at any point, regardless of their vantage point. So if we're taking temperature, for example, we could have two people standing in a room and everyone's going to agree that it's colder by the front door because it's minus 20 out. So your door is colder. Everyone agrees on it no matter where you're standing. You're standing in the far corner, you're standing right next to it. You could all take out a thermometer, one of your little laser thermometers, and measure the same temperature at the door. And then everyone's going to turn around and look toward the fireplace. Everyone's going to agree that the room is warmer at that location as well. So it doesn't matter where you stand in the room, everyone will measure the same temperature throughout the room. So that is a scalar field. Now, scalar waves get a little bit more complicated as far as definitions. So the two main things about a scalar wave is that they're nonlinear and they're non-Hertzian. So first let's talk about what is a linear wave. So linear waves, and I'm just going to do a broad description here, we're not going to get too technical, but linear waves are sinusoidal and they're described by equations where your dependent variable and its derivatives are at most the first degree. So there's a thing called a wave equation. If you're watching, I'm going to show this website that has it. It's called scalarpedia.org, and they have a very lengthy technical description of what linear waves are. But so there's a thing called a linear wave equation, and as long as any function satisfies this particular equation, it's called linear. And those are your basic waves, like sound waves are considered linear. Ocean waves are approximated often as linear waves. Electromagnetic waves are considered linear. So that's the first part. That's what a linear wave is. Now, Hertzian simply means that you are going to be able to measure these waves in the radar or the radio range. So their wavelengths are a few millimeters to many kilometers, but they're measurable. And they kind of basically measure frequency as hertz. So that's why they are Hertzian waves. So scalar waves are nonlinear. So they're not going to be described by that wave equation. And they are non-Hertzian. So they're not going to fall in this measurable range of frequency. And as we'll find later on, they're actually not measurable traditionally. So scalar waves are also called longitudinal electromagnetic waves, as opposed to transverse electromagnetic waves, which are your standard electric field, your magnetic field, any other sort of radiation, your light, your sound. Those are all considered to be transverse electromagnetic waves. Scalar waves are often called longitudinal electromagnetic waves. So in theory, scalar waves arise when you have two waves coming at each other. They're opposite in direction, so their vectors are pointing in opposite directions, and they collide or interfere with each other. So since their directions are opposite, the directions essentially cancel out, but the amplitudes do not. So that scalar portion remains intact. So you can still have an amplitude or a magnitude to this wave, but it's not moving because each of those directional vectors canceled out. So this means that it's basically a stationary wave. If there's no motion, there's no frequency, because frequency is how many wavelengths per minute or per second that you have. Well, if the wavelength isn't moving, there's no frequency. So it's a standing stationary wave. So you still have energy, but there's no movement. Okay. So because of this, it is thought that these scalar waves can act faster than the speed of light, or instantaneously. So sometimes you'll hear in quantum theory this action at a distance concept. This is something that Einstein had coined. And the actual action at a distance, the phenomenon has been seen, has been measured. And we'll find out later that it's not actually waves moving faster than the speed of light, but we'll get to that later. So scalar wave theory dates back to the mid-1800s with James Clerk Maxwell. So Maxwell is famous for developing the classical equations of electromagnetism. It's taught in every physics book. So his original electromagnetic equations contain these scalar components, but at the time the scientific community disregarded them because you couldn't measure these scalar quantities. They didn't seem to have any real physical meaning. So the scientists at the time figured it's just physically insignificant, so they didn't bother including them, because why study something that isn't really there, that doesn't really exist, can't be measured. So throughout time, Maxwell's equations just got boiled down to, I believe there's 4 of them, and they're just vector components. They don't have any of these scalar components. Now, Nikola Tesla, in around the late 1800s, 1899, 1901, I think, somewhere in that range, he got into these scalar waves and energies, and he wanted to study the scalar energy. This is what he thought would be that sort of energy that you could harness from the Earth, that it could be transmitted over long distances, essentially instantaneously, so there would be no power loss. These were these experiments that he attempted in Colorado Springs, and if you look him up, there will be tons of these huge Tesla coils. And this is what he was trying to do with his wireless energy transmission, was he was studying scalar waves. And in 1987, there was a CIA paper that was published. Well, it was just published, I'm sorry, in 2001. It was written in 1987 that talks about scalar waves. And just to quote from this paper, it says the scalar waves refer to non-electromagnetic waves with the potential for unconventional wave propagation. They may not attenuate like electromagnetic waves do. Their existence is not proven, but if they exist, their energy source is not clear. They have a quantum mechanical flavor about them. End quote. So that was from a CIA paper in 1987. So attenuation means to die off or to decrease in energy. So this paper says that they don't have that typical die-off. They don't lose energy like your normal energy wave does. Part of the problem with transmitting power over long distances is that you have an energy loss as you go from like your power station to your house. Just sending power down those power lines, you lose a lot of energy. So you have to have these power stations along the way to amplify and to boost up that signal every so often. With scalar waves, in theory, you wouldn't need that because there is no energy loss. And that's what makes scalar waves so interesting, is because if you didn't lose power and you could just transmit right from the power station to your house without losing any energy, that would be amazing. That would be something worth studying. And that's why everybody's into this scalar energy. It's why Nikola Tesla was trying to study and trying to figure out what this was. Okay, so we've talked a little bit about scalar fields and scalar waves. So here we are going to talk a little bit about scalar energy. So like we talked about above, we've got two waves that come together with opposite directions, so their vector components, their directional components cancel out, and you're left with this stationary wave that has some sort of magnitude, some sort of energy to it. So you still have this amplitude or energy, and that's our scalar energy. And again, it's thought that this energy radiates in all directions at once, instantaneously. So this sounds a lot like a concept called quantum entanglement, or action at a distance. And quantum entanglement is being studied by conventional, mainstream science. So it's a real thing that is being studied. And just briefly, a definition here of quantum entanglement. And if you're watching, I'm going to click on this one website here that has a really good kind of layman's description of quantum entanglement. It's at space.com, and I'll put all these links in the show notes. So quantum entanglement is when you have two particles that are basically connected in such a way that they react as one system, even if you separate them by large distances. And this can be light years. It can be billions of light years. It doesn't matter how far apart they are. They still interact as if they are still one system, still connected. And these can be any kind of particles, photons, electrons, anything subatomic. That's what they're studying, are subatomic particles. So again, even if you separate them by these huge, galactic distances, if you change one particle, a same corresponding change is noticed in the other particle, theoretically instantaneously, no matter the distance. And this contradicts your conventional physics because nothing can travel faster than the speed of light. So how can you change a particle here on Earth and then 18 billion light years away, at the exact same time, something else is happening related to your change here on Earth? It can't happen because light takes time. That information would take time to travel that distance conventionally. But theoretically, with our quantum entanglement, that doesn't happen. And it's been shown to not happen. And this is what Einstein called spooky action at a distance. They couldn't explain it. How is this happening? So he called it spooky action at a distance. So quantum entanglement involves the superposition of states of particles. So what superposition means is that you can take a wave function and you can construct it by adding up different, simpler wave functions. So basically you can take wave 1 plus wave 2 equals wave 3. And there's a very set pattern that you can add them up together and get this new wave function. So in quantum entanglement, each particle exists in any number of its states at the same time until you measure it. So this is one of these things where, if you've ever heard of Schrodinger's cat, the same sort of thing, where the cat is both alive and dead at the same time in a box. And you don't know until you open it. And once you make that observation, you've basically forced it into one state or the other. Until you make the measurement, that cat exists in both states at the same time. And one of my favorite applications of this concept was done in Futurama. If any of you know me, Futurama is one of my favorite shows. So in Futurama, they were at a horse race, and they have a quantum finish, and the professor gets really upset over their quantum finish. So let's take a listen to Futurama at the horse races.
And it's a dead heat. They're checking the electron microscope, and the winner is number 3 in a quantum finish.
No fair! You changed the outcome by measuring it.
So that's been one of my all-time favorite episodes, and just the concept that Futurama addressed this quantum entanglement thing. I love that. So here we are with the two. Sorry about this. Whoops. All right. So back to our quantum entanglement. So that's this idea that once you make a measurement, you've changed the outcome. Because particles, if they're entangled, they exist in both states. It's not just one or the other and you don't know. It's that they exist in the same state at the same time until you measure it. And that was something that I had never really considered. I thought it was one or the other. You just don't know. But that's not actually what quantum entanglement says. Quantum entanglement says that the particle exists in both states at the same time. Not one or the other, but both. So an example here in this article that I have pulled up here on space.com is that if you flip a coin and you don't look at it, you think it's either heads or tails. But the superposition principle means that it's heads and tails at the same time. And that one or other state doesn't even exist until you look at it. That superposition means it's in both states at the same time. So when you talk about this flipping of a coin, that's the idea of superposition when you have two states, your heads or tails, existing at one location. So both those states exist in one location. That's the coin in your hand. Now, quantum entanglement is superposition that takes place at two locations, separated by any distance. So you could have two coins being flipped, one here on Earth, one over in the Andromeda galaxy, however many light years away. And if you flip a coin here, whatever you get here will affect the coin out there in the galaxy. That's your quantum entanglement superposition. Two locations. So the example that most people will use here will be photons, because they actually will use photons in labs. And photons can be polarized, and polarization just means the direction of its electric field. So electric fields, as they move, can either move up and down or side to side, and that's a polarization. We can get into this later, but polarized sunglasses make use of this to block out part of that electromagnetic field from the sun. So you can take your two photons and you can entangle them or connect them so their polarizations are the same. So both of them have their electric field moving up and down or side to side. And then you separate the two, again, by any distance you want. And then when you measure the polarization of one photon, you'll find it to be, say, you did the up and down, the vertical state. When you measure the polarization of the other photon, it will also be vertical. And it doesn't matter, that state will happen at the same time. So I'm over here measuring my photon 1. As soon as I make that measurement, photon 2, no matter where it is, whether it's right next to me or whether it's 10 light years away, it will be in that same vertical state as soon as I make the measurement here on Earth. And again, that theoretically cannot happen with conventional physics, because if I make the measurement here on Earth, it's going to take some time for that communication to be sent over to the other photon to say, hey, be in the vertical state, that's where we are. With this scalar energy, that doesn't happen. As soon as I make that measurement, the other one, 10 light years away, already gets that information, already is in the right state that it should be. So you'll find that this is always the case, even though the results should be random, where if you're flipping coins, sometimes one will be heads, sometimes one will be tails. Sometimes both will be heads, sometimes both will be tails. But with quantum entanglement, every time you measure that one photon, the other one will always match that state, no matter what. And again, this is because they are entangled, so there is some communication between these two. And that's what is so perplexing. Now, conventional science has explained that entanglement does not actually violate relativity, because what's happening is that information is not being sent between the particles. Like, you're not actually making a phone call to the particle and telling it what to do. Scientists now think of entangled particles as essentially being one object. And a good explanation of this is given on, I'm going to click over here to this other website if you're watching, scienceexchange.caltech.edu. So this is a little more technical explanation of quantum entanglement. And in the 1970s, experiments tried to view the particles from different angles. So again, it's kind of a weird way to think about viewing particles, but if you look at a particle from a different angle, you basically get this different result. So that's kind of how they were explaining how you can have this entanglement and not violate relativity, this idea of the speed of light. So when the second particle was viewed from a direction different than the first, it was found to be in both states at once. So basically you can make your measurement on the first particle. What we just said was that as soon as you make that measurement, the second particle is automatically, instantly in that same state. What these experiments were finding out when you talk about viewing angle was that you can make the measurement on the first particle, but if you go over to your second particle and look at it from a different angle, you'll see that it actually is still in both of its states. It hasn't actually changed yet, even though that first one has been measured when you look at this different angle. So then when you measure the state of that second particle, then it might not necessarily be the same as the first one because you've got a different angle to view it. And it's very weird abstract concept. And like I said, this website here over at scienceexchange.caltech.edu has a pretty good description about it. So this was just one way that scientists have tried to explain these sort of non-relativistic effects. That it's not really sending information from one particle to the other, but it's basically one particle or one object that's kind of been pulled into two different locations. So it's very abstract, and I guess maybe it's because of my alternative theory loving nature, but I like the other explanation more. We're actually sending information faster than the speed of light, because the speed of light has been slowed down. I mean, you can pass light through some medium. You can pass it through glass, through water, through air with different temperatures or pressures, and it does slow down. It does change its speed. So is it really a constant? I don't know. I think maybe we could debate that. Okay, so this is our first overview of kind of the definitions of scalar energy, scalar waves, quantum entanglement. So from what I've seen, from the research that I've done so far, is that it seems like the term scalar energy gets used by sort of the alternative theory, alternative medicine groups, because scalar energy was also talked about in reference to like scalar energy lasers and weapons and these weird, futuristic weapons that conventional science says can't exist. So the conspiracy theory is that, they really do. We do have these weird space lasers and all these things using scalar energy. So scalar energy tends to get lumped in with kind of, weird pseudoscience. But if you say quantum entanglement, now people will accept it as real, true science. And to me, they're the exact same thing. Other than, scientists have tried to explain in a way that entanglement does not actually violate relativity. But, maybe that's the case. But to me, they sound like they're the same thing. Alternative theorists use scalar energy. Conventional theorists use quantum entanglement. And it just kind of seems to me that it's a terminology thing because people don't want to be seen as a conspiracy theorist, so they have to have a new term for it. And again, to my way of thinking, this has also happened when you talk about the ether and the Higgs field. So if you look up what the ether is, it was a term used by ancient scientists, ancient astronomers, to say that it's this material that fills in the region of the universe beyond our atmosphere. So the whole of outer space is filled with this thing called the ether. That's what the scientists used to say. It is also, again, back then was defined as a rarefied element, formerly believed to fill the regions of space. So that's what people used to believe, that there was this ether out there, kind of also referred to as the fifth element. So modern physicists, modern scientists come along and say, no, that's a stupid idea. There's no such thing as the ether. That's just pseudoscience. It's, that's what they used to think. We're better now. So what they have is a Higgs field. And the definition of a Higgs field is a field of energy that is thought to exist in every region of the universe. So whether you have the ether, which is a material that fills the entire universe, or you have a field of energy that fills the entire universe. To me, that's the same thing. There's something that's filling the entire universe. Ancient astronomers called it the ether. Modern scientists said, no, that's stupid. We need, the ether doesn't exist. Oh, but the Higgs field does exist. What is the Higgs field? It's this thing that fills the entire region of the universe. Just like the ether. It's like they just don't want to use certain words. Which is fine, but I think we should all be honest about what these things really are. So, is the Higgs field just the ether? I think maybe so. Is quantum entanglement just another name for scalar energy? I think there's a good argument for that case. And I think we will put a bookend on this, and next time we're going to go into the alternative theories about scalar energy, primarily as an alternative medicine. It's believed that scalar energy can have healing properties like improving your immune system, reducing inflammation, increasing energy, increasing oxygen flow, and there are these things called scalar energy pendants that people wear. So we'll talk about all that and just explore, is it real? Are these things all just scams? And I think that will be it for now, and I hope you'll join me next time when we talk a little bit more about this alternative scalar energy. So I'll put some show notes together, and they'll have these references, the CIA paper that we briefly looked at, a couple of these websites that describe scalar energy, and I think that's all I got for you for today. So if you have any questions, again, please contact me through the website, through the Facebook group, send me an email. Any way you want to get a hold of me. If you have any questions, you want to talk about anything specific, you have a specific question or concept you want me to look into, I would be happy to do that. So please let me know what you guys are thinking about. Tell me what you think about these episodes. If they're too long, too short, too stupid. I'm up for it all. Just be brutally honest. All right. Thanks for listening, guys. I will talk to you in about 2 weeks. Bye. So just to give a quick summary of what we covered in this podcast. First, in the lesson, we talked about mathematical notation and that the Greek letter delta means a change in quantity. The notation for a derivative is d divided by dt for most of our examples, and we'll often read that as d by dt. And we learned that velocity and acceleration are both derivatives. Velocity is a derivative of position. Acceleration is a derivative of velocity, which means that acceleration is a second derivative of position. We talked about vectors having magnitude and direction, and those would be position, velocity, and acceleration. Scalars only have magnitude. That would be distance and speed. And then we got into scalar energy waves functions. Scalar waves are nonlinear and non-Hertzian. They're also called longitudinal electromagnetic waves. They're stationary waves that have energy, and it's thought that they radiate energy in all directions instantaneously. Scalar energy has been studied since the late 1800s, with Nikola Tesla trying to harness wireless energy transmission in his Colorado Springs experiments. Maxwell's equations of electromagnetism contain scalar energy components, but they're no longer taught that way. Mainstream science seems to view scalar energy as pseudoscience, but has proven an identical concept, in my opinion, called quantum entanglement. Quantum entanglement is when two particles become connected and a change in one produces a change in the other instantaneously, no matter how far away it is. This involves a superposition of states, So a particle is in both states at the same time until it is observed. And as Professor Farnsworth from Futurama laments, you change the outcome by measuring it. Thanks for listening, guys. I will see you on the next episode. Bye. I hope you enjoyed this episode and are inspired to question and investigate the world around you. Let me know what you're thinking about. You can contact me through the website, theinterestedreader.com, send me an email at sarah@theinterestedreader.com, or join the Interested Reader group on Facebook. I'll see you at some later time T, where T is greater than T naught, and T naught is equal to now. Thanks for being an interested reader, and I'll see you next time.